Hey everybody, welcome back to my channel. Bienvenidos a todos. In this video, we're going to be talking about two things. We're going to look at parent functions. So we're going to look at the graphs of 8 basic parent functions and talk about what they look like. And then we're also going to then go in and look at 10 different transformations. So it's important for us to talk about the parent functions first, because we'll be applying the transformations to the parent function, so we need to know what the original graph looks like. And then when we go into the examples with the transformations, all of the examples are going to be on the simpler side because this is just an introductory video. So if you're new to learning about transformations, if you just started it in class or you're just brushing up on it and you need a good place to start, then this is a really good video to start with. Transformations can be really tricky and confusing because sometimes you do one thing, but if the number moves even just a little bit in the equation, it's an entirely different transformation. Sometimes it doesn't happen the way that you think that it does. So in the video, I talk about why that happens and give you some hints and tricks that you can remember that will help you iron out the details between what's happening in which transformation. This video, I'm going to be using a note sheet that I've typed up. If you want to print it off and follow along with me in the video, the link to that sheet that I'll be using in the video is in the description. So you can go and print that off before you watch this video and then fill it out along with me and have it to study and use as some notes. So let's get started. The first thing that we're going to look at in this video is the 8 parent functions, because these are the functions that we will eventually be applying transformations to. No particular order to which I'm going to go through these in, but let's get started. So the first function that I have here is the constant function, which has the form y is equal to b. You may use c or k. It is not really important what letter you use for y to be equal to, but this b just represents a number, any number. So for example, if that number were -4, the graph of that function would be a horizontal line that hits the y-axis at -4. So it would look like that. Note that if I would have chosen a different number here for the b value, then the horizontal line would have been in a different position on the y-axis, but the constant function always looks like a horizontal line. The next parent function that we have is the linear function. You may also hear this referred to as the identity function. Those are the same thing. And the linear or identity function has the form y is equal to x. And when you graph that function, what you will see is a line with slope 1 that goes through the origin. That looks like this. That is what the linear function looks like. The next function we have is the square function, which is y is equal to x squared. And the graph of the square function is a parabola. This is a quadratic function because the highest exponent that shows up is 2. And the graph of a parabola looks like a U with the vertex, which is where it changes from going down to going up, at the origin. Next, we have the cube function. Instead of an exponent of 2, we have an exponent of 3. And the cube function also goes through the origin. And the cube function looks like this. So in all of these examples, I'm just giving the general shape of what these parent functions look like. Next, we have the square root function, which is y is equal to the square root of x. And when we graph that function, we see something that looks like this. Notice that this function starts here at the origin. So that function in its original form does not exist anywhere where x is negative, because we cannot take square roots of negative numbers. The cube root function is y is equal to the cube root of x, so that's a little index of 3. Feels like a good time to mention that there is a little index of 2 on the square root function, but typically we don't write it. It's understood to be a 2 without writing it there. But for any other root, you would need to write the index like I did with the 3 for the cube root. And the cube root function looks like that. Notice I'm putting arrows on both ends of that graph. It goes on forever in both directions. The square root function did not do that. It didn't go on forever to the left. It started right there at the origin. The next function we have is the absolute value function, which is y is equal to the absolute value of x. And the graph of the absolute value looks like a V. It's made up of two different lines that meet at the origin and form a V shape. And the final parent function that we have is the reciprocal function, which is y is equal to 1 over x. This is probably the most maybe unfamiliar or the strangest parent function that we have. The graph of the reciprocal function consists of two different pieces. There's one piece there in quadrant 1, and then there's another piece down here in the third quadrant. And these 8 functions are our parent functions. Now, you may or may not, depending on your class, some of these you may have, some of these you may not have, depending on whatever course you're taking. But what is important for your parent functions is that you know the general shape of all of your parent functions, because when we actually go in and start looking at examples and start transforming the graph, it's going to be important for us to know what the original graph looked like. So now we are actually going to look at some examples. We're going to look at 10 examples. They each cover the 10 transformations that are summarized in this table. And what this table does is it gives us a lot of information. It gives us some graphical information, and it also gives us some algebraic information. So in this table, they all start with the original equation of y is equal to f of x. And that f of x is just some parent function. One of those 8 basic untransformed functions that we just talked about. And what the table does is it's going to tell us what happened graphically speaking. So when we look at the graph, what's the difference that we see in the graph? What happened to the equation? So just algebraically looking from the original parent equation to the new transformed equation, what's the difference that we see? And then back to a graphical illustration. What happened to the points on the graph? So if there was a point on the original parent function, where did that point go on the new transformed graph? So I already have this table completely filled out with the 10 different transformations. And instead of going through each of these rows one by one, we're just going to jump ahead and start looking at some examples, and the numbers in the examples correspond to the numbers of the transformation. So for instance, example 1 matches up with transformation number 1. So we'll go do the example and then we'll come reference the table to tie it all together. So in example 1, and in all of these examples, in fact, the parent function is going to be y is equal to x squared. This the parabola, the one that's shaped like a U. So I'll start off with a graph of what that looks like. I'll just label some points that are on that. The parent function goes through 0, 0. It goes through the point 2, 4. And another point that it happens to go through is negative 1, 1. And these are just some random points that are on the graph of this parent function. And it's going to help us put things into perspective when we start applying transformations to it. So the equation that we have here is y is equal to x squared plus 2. Y is equal to x squared plus 2. And if I were to graph y is equal to x squared plus 2, what I would see would be a graph that went through these points here. And the graph would look something like this. So just looking from the original black parent graph, untransformed, to the new graph that we have for the equation y is equal to x squared plus 2, we can see that the equation changed by the graph shifting up. Well, we can see that the graph changed by shifting up 2. Just from the black graph to the red graph, there was a shift up 2 units. How did the equation change? So that's asking what's the difference from the original equation to get to this equation. What did we do? Well, we added 2 outside of the function. And you'll hear me using the words outside and inside a lot throughout this video. So just a quick example, just so you can understand what I mean by outside versus inside. This would be an example of adding 2 inside the function, because I'm adding 2, but it's happening on the inside of the parentheses here. This is what's happening in example 3. That's happening inside. But that plus 2 right here, that's outside of the x squared. That's outside of the function, which is important because there is a difference between this and that. So we added 2 on the outside of the function. Now let's talk about how the points changed. Well, 0, 0 was a point on the original equation, but now the point 0, 2 is on the new transformed graph. 2, 4 was a point on the original equation, but now 2, 6 is on the new transformed graph. And then we also had the point negative 1, 1 on the original, it's supposed to be a negative 1, positive 1, negative 1, 1 on the original equation. But then on the new transformed graph, we have the point negative 1, 3. So what's taking us from these original points on the first graph to the new points on the transformed graph? Well, we are adding 2 to the y values because the graph is shifting up 2. And shifting up is going to change the y values since that's happening vertically. So everything that we've just seen in this example is covered in this first row of the table. When you add something, not necessarily 2, but any number k, to the outside of the function, you are shifting the graph k units up, and you transform your points by adding k to your y values. Now let's go take a look at example 2. Example 2, we have the same parent function, so I'll go ahead and sketch a graph of the parent function. I'm going to use the same points that I used before, 0, 0, 2, 4, and negative 1, 1. These are just some random points that are on the graph of the parent function y is equal to x squared. If I were to graph the function y is equal to x squared minus 2, it would go through these points and look like this. Still U-shaped, but now the graph has shifted down 2. So just automatically, what has happened to the graph? What was the transformation? That was a shift down 2. How did the equation change going from this equation to that equation? Well, we subtracted 2, and we subtracted it on the outside of the function. So again, because I was able to write that without parentheses, it's not minus 2 on the inside of the parentheses with the square. That's not what happened. The minus 2 was on the outside. That's why we're making that distinction there. And as to how the points change, well, instead of the point 0, 0, now we have 0, negative 2. Instead of the point 2, 4, now we have 2, 2. And instead of the point negative 1, 1, now we have negative 1, negative 1. So those points are changing by us subtracting 2 from the y values. So everything that we've seen in example 2 is summarized in row 2 of this table, where we subtract k on the outside of the function. The graph shifts k units down, and we change the points by subtracting k from the y values of the original points on the parent function. Now let's go take a look at example 3. So far in examples 1 and 2, both of those transformations happened vertically, and they happened outside the function. Here in example 2, that plus 2 is happening inside the function. I'll go ahead and sketch the original parent graph. So there's the graph of our original parent function, y is equal to x squared. If we were to look at the graph of the new equation, x plus 2 squared, we would see something that looks like this. The new graph has now been shifted 2 units to the left. So what happened to the graph? This was a shift 2 units left, or a shift left 2. Before we go any further, I want to point out here, this is one of the things that makes transformations so tricky. you see this +2 happening on the inside, and intuitively you think +2, you're going right, but that's not what's happening when you're on the inside of the function. Inside things happen counterintuitively. They happen backwards than what you would think they happen. So that +2 really does shift the graph 2 units to the left. How did the equation change? Well, the original equation was x squared, and the new one is x plus 2 in parentheses squared. And so I like to write that as we replaced x with x plus 2. So I don't just like to say adding 2 on the inside of the functions, and as we start looking at more complicated examples, I think that'll make more sense why, but I like to think of it as the original equation had x squared, but the new equation now has x plus 2, still inside the parentheses being squared. So the x was replaced by x plus 2. And then let's take a look at how the points changed. So the point 0, 0 was on the original graph, but now the point -2, 0 was on the new graph. The point 2, 4 was on the original graph. Now we have 0, 4. And the point -1, 1 was on the graph, but now we have -3, 1. So going from those black points to those new colored points on the second graph, we are subtracting 2 from the x values. And row 3 of the table up on this page summarizes this. When you replace x with x plus h, it takes the graph h units to the left. It doesn't necessarily have to be 2. It depends on whatever you put on the inside of the parentheses. And you get your new points by subtracting h from your x values. Now we're going to go look at what happens when the graph goes to the right in example 4. In example 4 here, we have the same parent function. I'll pause the video real quick and go ahead and sketch in that parent function. And if I were now to graph the new equation of x plus 2 squared, I would see that that transformation took the graph 2 units to the right. So now the graph would look like this. So I'll go ahead and fill in for what happened to the graph. What was the transformation? This was a shift right 2. Again, we have another example of inside things, horizontal things happening backwards than what we think. We see a -2 on the inside of the function, but that's really taking the graph right 2, even though your brain tells you to think that it's going left 2. That's not what's actually happening. That's part of what makes transformation so tricky. How did the equation change? We replaced x with x minus 2. That's how we're going from this equation to that equation that's underlined in red. And if we take a look at how the points changed, 0, 0 went to 2, 0, 2, 4 went to 4, 4, and -1, 1 went to 1, 1. So all of those points are transforming by adding 2 to the x values. Now it didn't have to be 2, it was only a 2 because that was a 2 right there. But more generally speaking, if we take a look at the 4th row in this table, when we replace x from the original equation, when it's just x on the inside of the function, when we replace that with x minus h, it takes the graph h units to the right, and we get the new points by adding h to our x values. So far, all of the 4 examples that we have looked at have all been shifts, either taking the graph up, down, left, or right. And all 4 of those examples use either addition or subtraction. So addition or subtraction is going to shift your graph in one of those 4 directions. The next 4 examples, examples 5 through 8, are no longer shifts. All of these are either going to be stretches or shrinks. And you could think of that as expansions or condensing, either one. Though you can use those words interchangeably, stretch with expand or shrink with condense. So let's go take a look at example 5. And as I'm scrolling to it, I'll mention that the stretches and the shrinks can be, I think, especially confusing because it depends on how you look at them, whether you want to call it a stretch or whether you want to call it a shrink. And I will explain what I mean by that specifically when we get to examples 7 and 8. But let's start with example 5. I'll pause the video again real quick and go ahead and sketch in the parent function. So there's our parent function, x squared. And just by the way, looking at just this equation, I can tell that the parent function is x squared because when I think of the 8 parent functions that we had originally, back towards the beginning of this video, clearly it's x squared is the one that I transformed to get me to 2x squared. And I transformed it with the 2 that's in the front. So that's just how I know that the parent function is x squared. If I were to graph the new function 2x squared, it would still go through the point 0, 0, but now instead of going through 2, 4, it would now go through the point 2, 8. And instead of going through negative 1, 1, it would now go through the point negative 1, 2. So the new graph would look like this. So what happened to the graph transformation-wise? This is a vertical stretch. Imagine that you're taking the original graph, this original graph here, and you're grabbing the top of the graph. Right here, you're grabbing both those arrows and you're grabbing the bottom of the graph. You're grabbing that vertex and you are pulling your hands up and down. You're stretching your hands further away from each other. So that's going to stretch that graph out vertically. How did the equation change? How did we go from that equation to that equation? Well, we multiplied by 2. And we multiplied by that 2 on the outside of the function. So just another quick example of why I'm saying outside here. There's a difference between multiplying x squared by 2 on the outside to give you a 2x squared and multiplying x squared by 2 on the inside to put the 2 on the inside with the x. These two things are not the same. They're not the same. So that 2 is happening on the outside. And now we'll take a look at how the points changed. Well, 0, 0 didn't change. 0, 0 is still at 0, 0. But 2, 4 stretched up to be at 2, 8. And negative 1, 1 stretched up to be at negative 1, 2. So what's happening to those original points to give us the new ones is that we're multiplying the y values by 2. That's how those points are changing. And all of that is summarized in row 5 of this table, scrolling back up to the table here, for a vertical stretch or a vertical expansion. You can use those interchangeably by some factor of a. Now note, it's important here that our 2 in example 5 is a number whose absolute value was bigger than 1. If the absolute value was not bigger than 1, then that would not have stretched the graph vertically. That would have shrunk the graph, which is what we'll see in our next example. But because it was a stretch, we're multiplying our y values by a, and that a is a number whose absolute value was bigger than 1. So those y values really are stretching out further away from where they started. Now let's go take a look at example 6, where we have a vertical shrink or a vertical compression. So here in example 6, we have the same parent function. I'll go ahead and sketch that in. So now that we can see the graph of the parent function, the graph of the new equation, 1/2 x squared, would still go through 0, 0. It would not go through 2, 4. It would go through 2, 2. And it would not go through negative 1, 1. It would go through negative 1, 1/2. So this graph now looks like this. And it might not be obvious from the graphs, but this new red graph is supposed to be a little bit wider. You can kind of see it as now the 2 point is not going all the way up to 4. With the x coordinate of 2, that's now further down at 2, 2. But the graph still did go through 0, 0. But it no longer went through negative 1, 1. That point right there is now negative 1, 1/2. So what's happening graphically speaking, what the transformation is here, is that this is a vertical shrink. This is a vertical compression. Shrink, compression, you can use those words interchangeably. How did the equation change? Well, we multiplied by 1/2. and we did that on the outside of the function. And I'm going to make a note here that 1/2 is a number that is smaller than 1. And it is only because 1/2 is smaller than 1 that we're getting that this is a shrink. Back up here in example 5, 2 was bigger than 1. That's what gave us the stretch. So it is important what number you're multiplying by here. And how are the points changing? Well, from 2, 4 to 2, 2, it's obviously the y values that are changing. The x values all stayed the same. The y values change because we're dealing with a vertical transformation, and vertical things affect the y coordinate. And there's two ways that you could think of this. You could either say that you are dividing your y values by 2, or you could say that you're multiplying your y values by 1/2. And those are the exact same thing. Dividing by 2 is the same thing as multiplying by 1/2. It's just a preference of however you want to think about it. I could have said the same thing up here. Instead of multiplying by 2, I could have said we were also dividing by 1/2, but we don't tend to think about things like that. And everything from example 6 is summarized in row 6 of our table. When that number, whose absolute value is less than 1, if that's being multiplied outside the function from like in examples 5 and 6, but if it's less than 1, like in example 6, you have a vertical shrink or a vertical compression. Emphasis on that less than 1. Same thing though, you are multiplying your y values by a. I want to take a quick second to talk about why both of these are the same, why they both say multiply your y values by a, if one was a shrink and one was a stretch. And really it goes down to the details of these inequalities. So let's just go back down to examples 5 and 6 and iron that out. In example 5, when we were stretching by 2, we were multiplying our y values by 2. They got bigger because 2 is bigger than 1. So multiplying by 2 gave us bigger numbers, so it really was a stretch. But here, where we had 1/2, we still did the same thing, and we could have thought of it as multiplying our y values by 1/2. But 1/2 is less than 1. So when we multiplied our y value of 4 by 1/2 to get the new y value of 2, that really did shrink the graph vertically. So you have to pay attention to what the factor is that you're using, what number it is that you're multiplying by, because that's going to tell you whether you're stretching or whether you're shrinking. So now let's look at example 7. Notice here, this 2 is happening on the inside of the function. I'll go ahead and sketch in the parent function, and I'll do it for both examples 7 and 8, just so I don't have to keep pausing it. Okay, so we have our parent function sketched in. I'm going to reference the same points we've been using. And now, oh, this is example 8. Well, let's go to example 7. Okay, so there are points labeled in. Let us think about what the graph of 2x entire quantity squared would look like. This graph would still go through the point 0, 0. It would no longer go through the point 2, 4. It would now go through the point 1, 4. And it would no longer go through the point -1, 1. It would now go through the point -1/2, 1. So now this graph would look like this. It would be a lot skinnier. And it would be skinnier because the graph has been horizontally compressed. This is a horizontal shrink or a horizontal compression. Now again, here we have that theme going on about things happening backwards than what we think. We see 2, which is bigger than 1, and we think stretch. But that is not the case when you are dealing with horizontal transformations. Horizontal transformations happen counterintuitively. They happen backwards than what you think they would do. So how did the points change? Well, our x values are what's changing here, because this is horizontal, and horizontal means x values. Horizontal runs this way, like the x-axis. And what's happening to those points is that we are dividing our x values by 2. You could also think of it as multiplying your x values by 1/2. That's the exact same thing. How did our equation change? How did we go from that equation to that equation? Well, we replaced x with 2x. And it was because 2 was bigger than 1 that it's giving us a shrink. Even though we would think stretched, horizontal things happen backwards. And all of that summarized up in the 7th row of the table. For a horizontal shrink or compression, you are replacing the x, it's happening on the inside of the parentheses, with ax, where a is a number whose absolute value was greater than 1, and you get your new points by dividing your x values by a, the same way that we divided our x values by 2 in example 7 to get those new points. Now let's look at example 8. Here we have a 1/2 on the inside of the function. I already have the parent function sketched. I'll go ahead and sketch in the new equation for 1/2 x quantity squared. This graph still goes through the point 0, 0, but it no longer goes through the point 24, and now goes through the point 44. And it no longer goes through -1, 1, and now goes through -2, 1. So this graph now looks like this. It looks a lot wider. It still has the same general shape. It's still U-shaped, but it's wider. So what's happening to this graph? This is a horizontal stretch. There we have again horizontal things happening not the way we think they do. 1/2 is smaller than 1, but this is really stretching. How did the equation change? We replaced x with 1/2 x. And how are the points changing? Well, how are we going from 2, 4 to 4, 4? The y-coordinate's not changing. This is a horizontal transformation. The y-coordinate's staying 4. We had 4 there and we had 4 there. It's the x value that's changing. And how did it change? Well, to get from 2 to 4, we're multiplying by 2. The x values. Or you could also think of that as dividing your x values by 1/2. Multiplying by 2 and dividing by 1/2 are the same thing. If you know anything about dividing fractions, when you divide by a fraction, you multiply by the reciprocal. So that's the same thing that's happening there. And all of this is summarized up in row 8 of our table. For a horizontal stretch, you need to replace x with ax, and that number a needs to have an absolute value that is less than 1, like 1/2. And you get your new points by dividing your x values by a. Now the thing you have to remember is that when you divide by a number that is smaller than 1, that is the same as multiplying by a number that is bigger than 1. Just a really quick example. If I take the number 7 and I want to divide it by 1/2, think about keep, change, flip, if you're familiar with that. To divide by a fraction, you change the operation to multiplication and you take the reciprocal of whatever the fraction it is you're dividing by. So you flip it. So here I am dividing by 1/2, but I'm really getting a bigger number because 7 times 2 over 1 is 14. So this really is giving me that horizontal stretch. Now the last two transformations that we have to look at are reflections, and both of these reflections have negative signs in them. Just depends on whether the negative is on the inside or on the outside. So when we eventually start looking at examples where we're combining more than one transformation, because so far in all of these examples that we've looked at, we've just looked at one transformation at a time. Eventually we'll look at some examples that have more than one transformation going on in the equation. The negatives always stand alone. A negative is always its own transformation. The graph of negative x squared looks like this. So just looking at that new graph, we can see that it still has the same general shape as the original graph, but it was transformed by being reflected over the x-axis. Now let's look at how the equation changed, going from this equation to that equation. Well, there's that negative on the outside, negative x squared, and I'm going to rewrite that just a little bit differently. I want you to see that that's the same thing as a -1 multiplied by x squared. So with that written now, I'm going to write that the equation changed by multiplying by -1 outside of the function. And that multiplication is happening on the outside of the function as opposed to the inside of the function like it is here in example 10. That's the last example that we'll look at. What's happening to our points? Well, 2, 4 went down to 2, -4. 0, 0 stayed at 0, 0. But -1, 1 went to -1, -1. So in all of these points, the x value is staying the same. But what's changing is the y value. And how it's changing is the y value is changing sign. So the y values are being multiplied by -1. You could think of it as multiplying your y values by -1 or by just changing the sign of your y value. And up in the table in row 9, both ways of that is written. Either you are... Oh, this is supposed to be a y. It'll be a y if you print the sheet out. Multiply the y value by -1. That's going to be giving you a reflection over the x-axis. So sometimes that can be a little confusing. People think that a reflection over the x-axis should change the x sign. But again, I'm just going to go off to the side really quick and just do a super quick example. X, y. If you think about the point, let's say -2, 3. Which is somewhere here in quadrant 2. If I reflect that point over the x-axis, it's now going to be down here. And what's that new point in green? That's the point -2, -3. So the x value stayed the same. X value is still -2, but it's the sign of the y value that's changing. We're going from a 3 to a -3. So flipping over the x-axis changes the sign of the y value. And if my little mistake here doesn't show you anything else, just know that math teachers make mistakes too. Okay. So now that we've looked at example 9, let's look at our last example, example 10. This is a reflection over the x-axis. So when I draw this new graph, we're not going to see any difference. Because if I take that original graph and I flipped it over the x-axis, it's going to look exactly the same. 2, 4 is still at 2, 4, 0, 0 is still at 0, 0, and -1, 1 is still at -1, 1. But the reason that is happening, let's fill in some information first. So what is the transformation? This is a reflection over the y-axis. I'll talk about how the points change in a second. How the equation changed is that we replaced x with -x. So this original x that was being squared, now it is -x that's being squared, and I know that because I have it in the parentheses. But in reality, what's happening here is that the point 2, 4, when it gets reflected across the y-axis, it's going to -2, 4. Which I don't have labeled on the original graph, but it is on the original graph. The point -1, 1, when it gets reflected across the y-axis, it's going to the point 1, 1, which I don't have labeled on the original graph, but it is on the original graph. And 0, 0 doesn't go anywhere because it is on the y-axis, and so reflecting it over the y-axis isn't going to move it at all. So the only reason that this graph looks the same is because the square function has symmetry over the y-axis, but what's happening to the points is that we are changing the signs of the x values. On some graphs it'll look different, on other graphs it will not look different. For example, if I had done the parent function of the square root of x, which if you think back to those 8 parent functions we had at the beginning, the square root of x looks like this originally. I'll just give us some points that are on it. 0, 0 is on it, and 4, 2 is on it, as well as 1, 1. Those are just some random points that I'm placing on the graph. If I look at what the graph of the square root of -x looks like, that's the same transformation that we just looked at in example 10. This negative under the square root inside the function is going to reflect the graph over the y-axis. So what the graph is going to look like now is it's going to look like this. The point 0, 0 stayed the same. It's still at 0, 0. The point 1, 1 is no longer on the graph. Now it's at negative 1, 1. There we have the x value changing signs when we reflect over the y-axis. The point 4, 2 is no longer on the graph. 4, 2 was over here. That's not on the graph anymore. The new point on the graph is the point negative 4, 2. There again, we have the x value changing signs. So that summarizes our very last transformation. So if you were able to print this sheet off, this sheet here, this table is a very good summary of the transformations that are happening. And the last thing I want to point out is I want to talk about some of the backwards things that are happening in these transformations. All of the things that happen backwards are things that happen horizontally. So for example, when I added this h on the inside to go left, that was on the inside, that was horizontal, that's backwards. Subtracting on the inside, that's horizontal, goes right. Let's look at the horizontal stretches and or shrinks. Multiplying this a to the x on the inside when it's bigger than 1 was a shrink. Doing it when it was less than 1 is a stretch. So everything that happens horizontally to the function is counterintuitive. And the last thing I'll say, just to provide some clarity with stretches and shrinks, because sometimes people can get confused with those, understandably so, because it depends on the way you look at it. Let's look at example 8. Just this function, 1/2 x squared, I could also write this as 1/4 x squared. So I squared the 1/2 to give me a 4th, and I squared the x to give me x squared. If we look at it this way, with the 1/2 written on the inside of the function, that's the horizontal stretch that we've already identified. But if I look at it this way, as a 1/4 on the outside, I would look at that 1/4, which is outside the function now, because I no longer have parentheses. Things that happen outside the function happen vertically. That would be a vertical shrink. So you could imagine here that going from this graph to this graph, you could either stretch the graph out horizontally, or you could shrink the graph down vertically. So horizontal stretches are the same thing as vertical shrinks, and horizontal compressions are the same thing as vertical stretches. It just depends on the way that you're writing the function. I'm going to be making more videos with some more complicated and more involved examples to give you some more practice. And if you had any questions about this video, feel free to let me know in the comment section below. I hope you enjoyed. If you did, make sure to give this video a thumbs up, like, and subscribe to my channel. I hope you found this video helpful. I hope it answered some of the questions you may have about transformations and parent functions. I'm going to be making some more videos on this topic that go into some more in-depth examples, so be on the lookout for those. And to make sure that you don't miss them, please make sure to subscribe to my channel. You can cut notifications on to be alerted when I post a new video. And if this video was helpful, please do give it a thumbs up and like it. Thanks for watching.